If we take the Laplace transform of a system before we go through the method of elimination, then we won't have to solve for C1 and C2 as we did in the first objective. So we're now going to solve a given linear system using Laplace transforms.
In this example, we have a system of two differential equations in normal form.
You'll notice we have the first derivative of x1, first derivative of x2, and we have two initial conditions. So we're going to start here by taking the Laplace transform of each side, and we get what you see right here. Notice x sub 1 at 0 is 1, so we have a minus 1 here. When we take it to the other side, it's going to be a plus 1. Laplace transform of the second equation, we get what we see right here. X sub 2 at 0 is minus 1, so we have a minus 1, or a plus 1. When we take that to the other side, we're going to get a minus 1 right there. So we simplify that, factor the coefficients of the x1 and the x2, get the form that you see right here. And if we multiply the first equation by 4 and the second equation by s minus 3, we can eliminate capital X1 and get an equation that involves only capital X sub 2. We simplify, write the solution for x sub 2, and we're going to use partial fractions so that we can take the inverse Laplace transform. Now you could use heavy side, or you could equate coefficients as we're doing here. Notice we have an AS plus a BS, so A plus B times S, for a constant 5A minus B. So we have A plus B is equal to minus 1, 5A minus B is equal to 7. Solve those two, and we get A is equal to 1, B is equal to minus 2. And we take the inverse Laplace transform and get x sub 2 of t. Now if we take our second differential equation and solve that for x sub 1, we have the form that you see right here. And we're going to substitute in for x sub 2. X sub 2 prime, notice it's e to the t minus 2 times minus 5, or plus 10 e to the minus 5t. So we simplify and get the form that you see right here. In the second example, we have x, y, and z. We have a system of three differential equations. First order x, first order y, and first order z. We have three initial conditions. So first of all, we take the Laplace transform of the first equation. What you see is right here. Notice x at 0 is 0. Second Laplace transform of the second one, we have what you see right here. Again, x sub 0 is 0. We have z of 0 is minus 2. We have a minus there, and we have another minus here, so three minuses. When we take that to the right, it's a plus 2. Then we take the Laplace transform of the third equation, substitute for y at 0, a 0, and we get the form that you see there for equation 3. Well, if we take equation 2 and just rewrite it right here, and we're going to multiply equation 3 by s, and then we're going to subtract equation 2 from equation 3 and eliminate our capital X and get s squared capital Y of s is equal to 1. Or we get little y at t when we take the inverse Laplace of 1 over s squared is equal to t. Now we're going to take that capital Y of s equal to 1 over s squared and substitute back right into here and get capital X of s, take the inverse Laplace of that, and get our x at t. Finally, if we plug capital X of s, the 2 over s cubed, into equation 2, we have the form that you see right here. And that gives us this, if we divide through by s, this form that you see right here. We can solve that for z and get z of t is t squared minus 2.